Last time in Under the Hood, we cracked the model open with gradient tape. We watched Autodiff compute every gradient by hand and ran a training loop we wrote ourselves. So, at this point in the course, here's a quiet, slightly uncomfortable truth. We have built 24 models, and not one of them has helped a single human being yet. They all live and die inside our scripts. Today, we fix that. This is the save and deploy stage of the pipeline, finally getting its own full episode, where a trained model stops being a Python object and becomes something the world can actually call. Every episode so far has ended at evaluate. We print an accuracy, we feel good, we close the laptop. But a model that only runs when you run it isn't a product, it's a science experiment. Deployment is the bridge from "it works on my machine" to a million phones can ask it a question. The first step is to get the model out of Python entirely. We do that with the saved model format. Think of it as a sealed language-neutral package. It contains the computation graph, the trained weights, and a description of how to call it. No Python required to load it. C++, Java, JavaScript, Go, they can all open this box. And that how to call it part has a name, the signature. A signature is the contract. It says exactly what the inputs look like, their names, shapes, and types, and exactly what comes back out. Callers on the other side of the world rely on this contract. Change it carelessly, and you break everyone who depends on you. The signature is the API. Now, how do we actually host it? Enter TF Serving, a production-grade C++ server whose entire job is to load saved models and answer requests. Fast. It handles batching, it load balances, it serves multiple models at once, and it watches a folder for new versions. You don't write a Flask app and pray, you point TF Serving at your model directory and it does the rest. Once it's running, your model is an endpoint. You send it JSON over HTTP, a plain REST post, and you get predictions back as JSON. Or if you need lower latency, gRPC. Either way, the model that lived in your script is now a URL. Any service in any language can hit it. But sometimes you don't want a server at all. Maybe you want zero latency, total privacy, and no cloud bill. That's TensorFlow.js. You convert the model once, ship the files to the browser, and inference runs on the user's machine, on their GPU, with their data never leaving the page. The same trained weights, now running in JavaScript. There's one more thing TF Serving quietly gives you, and it's the thing that lets teams sleep at night: versioning. Your model lives in a numbered folder, 1, then 2, then 3. Drop a new version in and Serving picks it up. If version 2 is worse, you roll straight back to 1. Safe to move forward, safe to move back. Let's open 26serving.py. It's short because most of the work is one-line commands. Page 1 exports the model and inspects the signature. Page 2 serves it over REST and converts it for the browser. We'll walk it section by section. We start by loading the model we trained earlier, a small binary sentiment classifier. And then the star of the show, model.export. Note the path, saved model.1. That trailing one isn't decoration, it's the version number TF Serving looks for. Export writes the saved model with the default serving signature inferred from the model's call. Notice we don't say model, save, thing.keras. Here, that's the Keras checkpoint format, great for resuming training. Export gives us the deployable language-neutral package. Now we inspect what we just wrote from the command line with saved model CLI show. We ask it to tag set serve and the default signature. It prints the contract, an input called inputs, a float tensor of shape negative 1 by 20. The negative one means any batch size, and an output, a single sigmoid probability per row. One thing to flag: when Keras exports, it renames the tensors to generic handles. The input becomes inputs, the output becomes output 0. That's the exact JSON shape our callers must send. Read this before you write a single client. Here's the serving command itself. In production, this is a Docker container. In the script, it's one line, point tf serving at our base path, name the model, expose the REST port. Notice the base path is the folder above the version number, saved model, not saved model not one. Because serving manages the version folders itself, the moment it's up, localhost 1 is live. And here's the call, a curl post to the models.predict URL with a JSON body that has one key, instances, holding a list of input rows. Send one example, 20 features. The response comes back, predictions, a list, one probability per instance. 0.96. That number used to live in a variable. Now it lives at a URL. Last section, the browser. TensorFlow.js converter takes our saved model and emits a model.json plus binary weight shards into a web folder. Then the 5 lines of JavaScript import tf.js load graph model from the URL. Note graph model because a converted saved model loads as an inference only graph. Build a tensor with the same shape the signature demanded. Call predict and read the result back. Same model, same weights, same answer. But now it's running inside Chrome on the user's device with no server in the loop at all. And that's deployment. One trained model, 3 destinations, a sealed saved model package, a REST endpoint behind TF serving, and a tf.js bundle running in the browser. Version folders let you roll forward and back without fear. But notice what both of those serving paths assume: a real machine with real memory. TF serving wants a server, even the browser wants a decent laptop. So what about the device in your pocket with a tiny chip and a battery to protect? Next time, AI in your pocket, we shrink the model itself with TensorFlow, Lite and quantization until it fits on a phone.